Thank you very much for the kind introduction, and thank you for the invitation to come here and speak. It is wonderful to get to speak to what I consider to be sort of a sister community just above us architects in ye olde stack. So in particular, I am an architect. And the way I view my field is that we sit in the middle and act as a mediator between application trends that are coming at the field from one side and technology trends that are coming at the field from another side, and we try to balance the forces of those two and come up with good ways to navigate the challenges and opportunities that they represent. So on the technology trends side, you probably have heard about, it's pretty much de rigueur that you have to talk about the end of Moore's Law. But I thought I would start by talking about the beginning of Moore's Law first. So just over 50 years ago, Gordon Moore wrote a paper. If you haven't read this paper, I suggest you go back and read it just to see what was what back then. The paper was about understanding the cost trade-offs of cramming more components, more transistors onto integrated circuits. And for those of you who are experimentalists in the audience, check this out. He had basically two graphs in the paper. The one on the left has an x-axis that is the number of components, that is transistors per integrated circuit, and a y-axis that's the log scale of the relative cost. And those different U-shaped curves are different years that he was projecting the cost for. And the idea is you would pick the minimum cost point to operate at, and if you draw a vertical line down from the lowest point of the U, you'd find out how many transistors that minimum cost point would represent. And then you can plot that on the second graph, which is years on the x-axis and number of transistors on the y-axis. And you take a few data points, but you'll see not very many data points. You draw a line, and thus a 50-year exponential is born. It's really sort of a hallmark of confidence, among other things, that this has lasted as long as it did. So why did it last so long? It lasted because there were benefits that came from the sort of virtuous cycle that was created as more transistors came along, more performance came out of it, which led to more revenue, and so on and so forth. So it's a business law more so than a physical law. And from that, we've had decades of Moore's Law scaling. The upper scatter plot that you can see here are the sort of transistor scaling numbers over years from 1970 to essentially the present. But you can see that other metrics also scaled. But you can also see that things are not quite keeping up anymore. In particular, single-threaded performance, clock frequency, and power all started to level off about 15 years ago. Basically, when we started hitting fundamental power limits. The other thing you can see is that our response to it was, among other things, to start going for different types of on-chip parallelism. So first, homogeneous parallelism, increasing the number of logical cores, and subsequently shifting to more specialized approaches, more heterogeneous parallelism. Which brings us here. So we have heterogeneous parallelism at essentially all levels, from IoT devices to mobile to data center. The diagram that I'm showing here is a TI OMAP 4. Just as one example of this is something that you'd find in a lot of tablets. What you can see across the top are a number of different compute elements. On the upper left in yellow are a bunch of ARM cores. So there's already sort of general purpose parallelism there. But the rest of those blocks across the top are specialized processors for digital signal processing, audio processing, graphics processing. There are face recognition units that are just circuits that just know how to recognize faces, and so on and so forth. So this is sort of where we are on the technology side. Trends like slowing in Moore's Law and the end of its partner scaling trend of Dennard scaling together have left us with no choice in terms of power performance trade-offs except to go here. And it's a challenge in terms of figuring out how to navigate the way forward from this kind of a spot. So let's look a little bit at application trends because they're pushing on heterogeneity as well. So if you look at how we're using computing devices today, they're essentially everywhere. They're highly distributed. There's sensor networks out in the environment. There's sort of industrial sensing as well. Across all of this, it's deeply data and communication intensive, and there's massive heterogeneity in the types of devices as well. So what does that mean from a sort of hardware-software interface standpoint? We see these applications getting programmed by a huge variety of people, not all of whom are sort of the folks that you gave an A to in your programming language class. And also there are a lot of black box implementations. So for example, if I buy an IoT device like a smart front door lock, I'm asked to trust as a consumer that that smart front door lock was written and the software was written and the hardware was designed by people who appreciated the subtleties of race conditions that might result from me and my husband or my housemate messing with that device at the same time, concurrently on top of an eventually consistent replicated data store someplace in the cloud. So there are a lot of subtleties and concurrencies in these kinds of systems, and there's a profound amount of trust that we're being asked to place in them, either as consumers or in industrial or sort of safety critical systems. Even well-versed designers in this ecosystem may not be allowed to see the sort of details of other parts of the system in a way that helps them navigate everything they need to know in order to model these systems, measure them, verify them, and so forth. So that brings us here. There's heterogeneity in the large, this sort of vast diversity of devices that we're programming towards across many different vendors with many different hardware-software interfaces in play. And at the same time, there's heterogeneity sort of in the per-device world, that picture on the bottom, where we might see as many as a dozen different instruction set architectures on the same chip, and a bunch of units like accelerators, like that face recognition unit, that don't even have an instruction set architecture at all. So we've lost that sort of abstraction from these chips in many ways. There's also heterogeneity in the memory hierarchy, which is the lower half of that bottom plot. And there's also heterogeneity in the memory consistency models, which I will talk about in a moment. So we talk a lot about Moore's Law and how it began in the mid-60s. One thing that we talk less about, but it's sort of worth remembering, is something else was born in 1964. Well, I was too, but in addition to Moore's Law and me, computer architecture was born in 1964. And so it was actually the paper that I show the front page of on the right is a seminal paper by Amdahl, Blau, and Brooks that laid out the concept of an architecture for IBM System 360. And there's a footnote for that paper, which I've enlarged. So basically, the story is that they sort of went around and around about different words to use in the title to refer to IBM's plan that they were going to have a single, durable hardware-software interface under which they would have different implementations of the machine that they could sell at different price points. And so architecture at that point was, they had a notion of it being a sort of long-term plan, but they also had a notion of it being sort of for different cost points of the moment. But it really established the value of hardware-software abstraction. And it was a good thing, and we had a half century. It was fun. But I think we're at a fundamentally disruptive moment right now. So instruction set architectures, obviously we still have a lot of x86 code in the world. We still have a lot of code that's compiled for different ISAs. They are still useful. I'm not saying they will go away fundamentally, but they are offering less and less relevance for us as a durable, long-term abstraction layer. And so what are some examples of this that you can see? The Apple AA processor, which is now a little bit out of date actually, it represented the tipping point where over half of the chip area of that processor was actually devoted to circuits that were not sort of fundamentally processors per se, but were specialized accelerators that you would access through APIs and so forth. Likewise, other companies are taking the choice of taking their ISA and hiding it underneath other abstraction layers to try to discourage you from relying on it in any sort of long-term way. So we still have ISAs, but it's a time to really stop and think. How are we going to move forward and program these deeply heterogeneous systems if the hardware-software interface keeps changing with essentially every new chip generation? Even worse, how will we verify them? Because if so much is changing both in the hardware and the software at the same time, what do we verify against? And how do we overall manage the complexity of what we've created, where we know how to build, we are building these deeply heterogeneous chips because it's what we know how to do to meet certain power performance targets right now. But we really don't have a good way forward in terms of long-term ways to program them. And when I say we here, I'm mostly speaking as an architect. I'm hoping that the you part of the we will help find some answers or are already progressing on this. So we're entering what I would call a post-instruction set architecture world, where that interface is devalued or challenged in different ways. So that's the problem. If you are an optimist and you want to see an opportunity in this, then I would say that the opportunity is that we have a good moment now to think about and design new practices for our field around new interface layers. And so the question is, can we define and design these new interfaces and techniques and metrics and so forth around more modern design goals that go beyond performance and into the other things that we know are important, but we maybe haven't valued so much thus far. So in terms of metrics, I just wanted to pause here. If you go back into the 50s, you can tell that designers of systems clearly cared about reliability. There's a fabulous quote from Morris Wilks, who's sort of a titan of computer architecture, one of the early Turing Award winners. But he has this great quote that says, I realized at that moment the full force of what lay ahead of me. I was going to spend the bulk of my time debugging my own software. So here he was as an architect, but he recognized that reliability and debugging and programmability were going to be major influences in his life. That was the 50s. Now, I will not say that we went totally performance obsessed in the middle, but we did get a little bit performance obsessed in the middle, especially in architecture, I would say. We were encouraged, and rightly so, to pursue a quantitative approach, and that was a great thing to do. And I'm 100% with it. I just think we should try to take that quantitative approach and bring it out to as many relevant and important metrics as we can. And so I see us sort of going forward into a much richer set of metrics and understanding how we can design systems, both hardware and software, with more metrics in mind. And I'll just pause and say, well, why didn't we already do this? Have you all heard about sort of looking where the light is good? So the story of this picture is the fellow loses his wallet on a dark street, and so he sort of stops underneath each street light to see if he can retrace his steps and find his wallet. And people ask, well, why are you only looking under the street lights? And he says, well, that's where the light is good, right? So we had a sense, we knew how to quantify performance, and so we did. Unfortunately, right now, to a large degree, some of our sort of design practices are revolving around what is easier to measure or model rather than by what we actually want to achieve. And I'm not saying this is sort of an all or nothing thing, but I do think that there's a chance now to sort of reweight back towards other metrics. So I'm going to sort of go down the path of talking about a couple experiences we've had in my group of sort of taking this journey from being performance obsessed 25 years ago to sort of pushing hard on power maybe 20 years ago to now looking at other metrics such as correctness, security, and so forth. And the first story that I will tell is about me being dragged physically back into memory models. So I was a grad student 25, 30 years ago, and at that time there were a lot of large-scale projects to build parallel computers. And I was in one of the groups in which some of the work from 25 to 30 years ago by Kourosh Garashoglu was being hashed out about weak memory models. And I remembered some very long group meetings where we sorted through the details of memory consistency models. And so when my student came to me about 5 years ago and said, we should work on memory consistency models, this is Dan Lustig, who's now graduated and doing wonderful things. I said, oh my gosh, you're not going to pull me back into that, are you? And he said, no, it's really important. We really should do it. He was right. It was really important. I'm glad we did it. I will also say that I made one stipulation. We have to automate this because I can't deal with any more of those meetings, right? So we set out to come up with a way to let people verify, study, and design for memory consistency models without the sort of traumatic stress that I experienced 30 years ago. So here we go. A lot of you know the basics of this, but I will sort of give it just for breadth. So correctness is the issue that we're studying here, and memory model verification is the specific of it. And as many of you have learned in class, sequential consistency is where this begins. So Lamport defined these two rules for concurrent execution. You're sequentially consistent if the memory operations of each processor look as if they happened in program order, and if the memory operations across processors of all processors look as if they could all agree on some global sequential order. And so for the tiny little program on the left there with 2 threads and 2 instructions per thread, there are 6 legal executions. There's 6 ways of interleaving those instructions that maintain program order within threads and that let all the processors agree on some global order. And that would be nice, but there's a lot of hardware sort of microarchitectural optimizations we would like to do for which we cannot naturally sustain sequential consistency. So for example, you probably learned in your architecture class about store buffers. And store buffers cause a processor to not naturally be sequentially consistent anymore. Because if I can sneak a peek, if I can write something into a store buffer and then sneak a peek at that stored item before the rest of the world can see it, then how could we possibly agree on a global sequential order for things if I'm sneaking peeks at things earlier than everyone else? So over the years, other memory consistency models have come out. TSO, or total store order, is an example. Here's a chunk out of Intel's documentation on total store order. In particular, TSO lets you have a write buffer because here all we have to agree on is the global order in which the stores appear to have occurred, not all instructions. There's a few things to take away from this slide. So first of all, the amount of documentation is considerably longer than the 2 rules on the previous slide. And second of all, this documentation is written in English. So it's a natural language specification. And therefore, it can be hard to get through all the subtleties in a sort of formally specified, formally verified way. That's foreshadowing of some stuff that we'll sort of embark down in a minute. If nothing else, one of the things that I think I sort of pause to say at this point is a lot of people, especially students, feel like, shouldn't we have figured this out by now? Basically, memory consistency models are the specification of what value should be returned when your program does a load. And there's a sense in the world that surely we should have figured this out by now. Unfortunately, we really haven't, or not fully. And so it's important to specify and verify them as these systems become more complex. And again, as we have a half dozen or a dozen different instruction set architectures on a chip, each speaking often a distinct memory consistency model. So a little bit more about why verifying these memory models is important. Sort of what can go wrong. Obviously, if your program load comes back with the wrong answer, you can get incorrect software answers, you can get unreliable operation, and it can also lead to security exploits. In terms of what can go wrong across the layers, the thing that is really remarkable is there are different places that things can go wrong, from the high-level language memory model to an inadequate sort of instruction architecture specification of what it is promising at that hardware-software interface. The compiler that maps from one to the other, that can go wrong. And even if all of that is correct, we could have a design error in the hardware that just says, we were trying for TSO, but we didn't quite make it. So incorrect hardware implementations can go wrong as well. So my group, and in particular, Dan Lustig, who I mentioned earlier in this story, had a particular goal that he wanted to do. He said, instruction set architectures specify the memory model, but we really don't have very good ways of checking that a particular piece of hardware, a particular pipeline is actually implementing correctly that specification. And so we wanted to verify the blue against the green. End of story. Over the years, we've built a full stack of tools that try to verify all the way from high-level languages up top, down, and actually reach now to Veralog designs, register transfer level at the bottom. Across these tools, I'll talk in more detail over the next few slides, but the one-slide version is we start with an axiomatic specification of the implementation at some level, and we translate that automatically into a set of happens before graphs. So you can see on the right an example of one happens before graph layered to show that there actually could be several happens before graphs to consider all the different cases, all the different interleavings of some scenario. The thing about a happens before graph in sort of the one slide version is if A happens before B, I can draw an edge between them. If B happens before C, according to some axiom, I can draw an edge there. If C happens before A, I can draw an edge there. Here's the trick. If A happens before B, B happens before C, and C happens before A, then A is happening before itself. That's physically impossible. And so anytime we can find a cycle in a happens before graph, we have verified that that particular scenario cannot physically occur. And so essentially, if something is forbidden by a spec, then our game is to show that for all possible happens before graphs, there is a cycle in them. If we find an acyclic happens before graph, then the scenario is observable. And if so, if it's allowed, fine. But if it's observable to us and yet was supposed to be forbidden, you can give it back to the designer and say, you might want to know about this. So a little bit more detail. So what the prior work had done, and there was a fair amount of sort of formal languages and compilers work, including much from this community and Popl and so forth. The prior work had essentially usually stopped with happens before graphs at the instruction set architecture level, and each node in the PL world's version of a happens before graph was a single instruction. But we're architects, so we wanted to unpack that a little more. And so in our world, what you can see is a happens before graph on the right that is trying to depict aspects of behavior of that simple pipeline on the left. So this is the 5-stage pipeline from a typical sort of undergrad computer architecture class. The happens before graph on the right has columns of nodes. Each column corresponds to one instruction. And each of the nodes in that column corresponds to some microarchitecturally interesting aspect of executing that instruction. So for example, fetch, decode, execute, and so forth are depicted separately in our happens before graphs. The happens before graphs are specific to a piece of code. So for example, in this case, it's a simple message passing litmus test that we're depicting with the two columns on the left being thread 0 and the two columns on the right being thread 1. And we start with essentially no ordering assumed, but each time that we process some of the axioms that describe this microarchitecture, we can add new edges to the happens before graph to show something we've learned about the ordering of events. So the key goal is to get the nodes associated with individual locations in a microarchitecture rather than having a node that is for the instruction as a whole. A second thing that we did that's a slight shift from some of the PL versions of this is simple unlabeled edges. So we can do fully transitive analysis. There's some prior work where you couldn't just sort of take the transitive closure of all of the edges and look for cycles. By taking the transitive closure of all the edges and looking for cycles, we actually can keep this analysis quite fast. Most of the stack that I showed you executes in seconds or minutes for many of our tests. And so it becomes an interactive part of an architect's design process rather than something you'd imagine at the way last part of a design. And again, acyclic corresponds to observable and cyclic corresponds to not observable. So let's zoom in a little bit more on this piece of it. So here we are, zoomed in. We can have an axiom that describes something we know about fetch. We're going to say that fetch is going to happen in program order. And so we can essentially ask to add an edge for all I1, I2 between the fetch stages of those two. Likewise, we can say that if fetch happens in order, in this microarchitecture, decode is going to maintain that ordering. And so we can write a separate axiom that says, if fetch happens in order between I1 and I2, then decode will also. And so on and so forth. This very simple architecture has about 12 axioms. We have built up much larger axiom databases that cover, for example, Intel's Sandy Bridge processor and the relevant parts of the Linux virtual memory system so that we can compose together aspects of operating system behavior with hardware behavior as well. So you can do this at scale. For all of you who are sort of language designers or the like out there, I will say, I'm an architect. Like, is this pretty? I don't know. It works. So I'm not claiming that this is the sort of perfect way to express the interface, but what I'm claiming is that this is the kind of interface that I think more of our systems need right now. Some of the interesting things is, as I said, we're not just going to have a single happens before graph. For the given test case, we're going to enumerate all the possible scenarios that could occur. So that's multiple happens before graphs, essentially enumerating all possible interleavings, including the fact that there are ways in which, for example, the source of a load could come from different places. We might get it from cache, we might get it from the store buffer. We're going to enumerate both of those possible cases and check them both. So one of the nice attributes of this approach is that the axioms are independent contracts. So we can essentially trust the overall model by trusting each of the axioms individually. And if we find a bug in the design, if we say, hey, here's a case where you're allowing something to be observable that shouldn't be, the designer can figure out what's the axiom that needs to be added, what's the design change that needs to be imposed to create an edge in that case. And so it allows both more tractable verification problems, and also it allows, we argue, an easier way for the designer to learn about issues in their design and fix them. So there, essentially you can think about it as different paths through the microarchitecture are provided for different reads, writes, and so forth, different categories of instructions, and then also different sort of per pipeline stage orderings that we need to consider. So I'm not going to go deeper and deeper and deeper into the different tools in that stack overall, but I will say that we have sort of at this point gotten this style of very hardware-aware happens before graphs to cover a pretty broad range of types of scenarios. In particular, we can handle memory hierarchies, where you might be getting data from different parts of a cache hierarchy. We have a notion of a value in cache lifetime, or VICL, that lets us reason about different ways that something might have been evicted from the cache or not. And that in turn lets us verify things at the coherence consistency boundary, such as lazy coherence approaches. We have also, as I said, come up with composable techniques for verifying things that are partly in hardware, like the microarchitecture, and partly, say, the control of the operating system, so that we can do address translation aspects of consistency verification, where some of the axioms are provided by the operating system designer, and some of the axioms are provided by the processor designer, and they compose together. And so as an example of a graph that we can generate and analyze and verify that you would not want to stare at on your own, I've shown this one. This is from our TryCheck work that does the hardware OS boundary. In this, we have, as I mentioned, a fairly intricate Sandy Bridge pipeline. That's the different rows of the graph. The different instructions are a mix of user-level instructions, plus system-level instructions in the litmus test, plus what are called ghost instructions in our work. These are things that act as instructions inside the processor, but are never fetched, decoded, or executed. And the best example of this is that if I miss in the TLB and I need to do a page table walk, there's actually hardware in the system that is issuing memory references on behalf of the hardware page table walker without ever fetching or decoding them. So those are implemented and consistency checked in our system as if they were fetched, decoded, executed, even though they aren't. So it allows us to consider intricate timings that go across the hardware-software interface. So one thing that we wanted to do as we move towards this full stack view of the world was to come up with good full stack examples to demonstrate the work. This one is something that Jad Algalov studied and sort of wrote about in 2011, and I'll use it as a motivating example. It's also a motivating example not just for sort of verification, but for specification writing as well. It's a cautionary tale. Okay, so the ARM instruction set spec was ambiguous regarding same address load-to-load ordering. Now, if you have photographic memory and you can sort of go back 15 slides to the TSO spec that I showed at the beginning of the talk, you might remember that the first bullet of the TSO spec says that loads shouldn't be reordered with each other. They have to maintain load-to-load ordering. The ARM instruction set architecture has a weaker memory consistency model, and it was in particular ambiguous regarding whether that load-to-load ordering needed to be maintained or not. If something's ambiguous and you're a compiler writer, you might presume, I don't need to do it, right? Meanwhile, the hardware people are looking at that same ambiguous spec and saying, well, if load-to-load ordering doesn't matter, then I'm not going to design my whole processor to do it. So they both sort of are staring into the abyss from opposite sides, and not surprisingly, neither side did it. And the issue is that actually high-level languages have memory models, and in particular the C++ variables with atomic types required that same address load-to-load ordering to be correctly implemented. And so Algalov gave the original example of this for ARM v7 instruction set. In our group has a video that you can check out where we show this bug actually being exposed in the wild on a Google Nexus 6 phone. That's a little bit of a dated phone, but you can still buy them used, and we did. So in particular, the code on the right is all it takes to exercise this bug and expose it. So what did ARM do? So this is a case where you could either say we should fix all the compilers, or you could say we should fix all the processors. Our stance is it's not super material whose fault it is, but it's important to be able to verify these things across the full hardware-software spectrum. In this case, ARM didn't want to recall a ton of processors, so what they did was they asked for compilers to be rewritten to insert those fences, those ordering instructions at the right places. There's some performance penalty associated with that. But the key thing is that the ARM instruction set actually had the right fence available. It was just a matter of asking the compiler people to insert it. Keep that in mind because that will come up in a few slides. So in more detail, what are the different levels of this? Top level is that C source code for the exploit, or the sort of bug generator that I showed from the previous slide. At the bottom level is some specific CPU you're running it on, say an ARM Cortex A9, which is one of the processors on which you can demonstrate this bug. In between that are a set of compiler mappings that get you from the high-level language to the assembly code. And then, obviously, from the assembly code, you run it on a particular processor. We wanted to be able to check those different levels comprehensively, and so that brought us to this TryCheck tool that we published at ASPLOS about a year ago. And the way TryCheck does its work is the following. Down low in gray are those microarchitecture level models that I spoke about before. So a set of axioms, a set of instruction set architecture litmus tests like the one I showed, and the output of that is a set of happens before graphs that say something is either observable or unobservable. Way down low in hardware with all of the pipe stages modeled in all of that grungy detail. Way up high, we have high-level language litmus tests. For example, C-level litmus tests that are testing different atomic sequences. And we can use a higher level language memory model or simulator to determine for those litmus tests which outcomes are permitted and which outcomes are forbidden. In between the two are a set of compiler mappings that get you from the high-level language down to the ISA level litmus tests. on the left. And the key outcome of all of this is what's shown in that two-dimensional table, that four-celled table. So we have the low-level hardware stuff saying whether something's observable or not, and we have the high-level, essentially the spec, saying whether something is permitted or forbidden. And so if the high-level spec says that it's permitted, and the low-level verifier says it's observable, we're okay with that. That's the upper left green box. If the high-level spec says that a particular outcome is forbidden, and our low-level hardware model says that it's never going to be observed, that is, every single check we make is cyclic, then that's also okay. The upper right cell of this box is the case where the high-level spec says it's permitted, and the low-level hardware says you will never see it. That's okay, that's overly strict. So for example, if I want to have a TSO processor, but I implement it in a very simple in-order way with no write buffer, I've actually implemented sequential consistency. It's stricter than it needs to be, but it's legal for TSO. So that's the yellow box. You might be leaving some performance on the table, but you're okay. The red box is the interesting one. So that's the case where the high-level spec says that something's forbidden, and our low-level hardware checker says, hey, this is observable. Here's a case of an acyclic happens before graph that will expose this bug. The key thing from our point of view as architects is that we can do that analysis in seconds or minutes. It's fast enough to iteratively refine the design. It's fast enough to decide sort of how you might want to nudge the instruction set architecture or the microarchitecture to make changes. And so having worked in sort of Poweraware computing for a long time before this, my analogy is that there was a point around the year 2000 where architects didn't do power. Power was a late stage thing that some circuit person would verify just before you taped out the chip. And we said, no, if architects get in on the power game, we can have higher leverage earlier in the design process to make more fundamental, more meaningful changes. And so what we're trying to do here is pull verification earlier as well. So verification right now, for a lot of hardware people, is the thing that you do just before you tape out a design. And we would like to get more of the hardware world to think about it earlier on. It's not to say it's been ignored, but it's to say it isn't prominent, it isn't sort of culturally as common as some other things in architecture. So one of the case studies that we worked on at the time we started this work, which was about 1.5 years or 2 years ago, the RiskFive instruction set architecture was in the process of being released with a draft specification. And so we took the draft specification of this instruction set architecture, and we came up with 7 possible pipeline implementations for it, all of which are legal. They abide by the spec, or the draft spec at that time. But they varied in how they were implemented. So some in-order pipelines, some out-of-order pipelines, with a write buffer, without a write buffer, and so forth. And then we did the full TryCheck mapping from high-level C litmus tests through compiler mappings and down to these different 7 hardware options. The thing that we found was that, so RiskFive spec, first of all, wasn't very clear in some places. It was ambiguous as a spec. But even when you made sort of reasonable choices about it as a spec, you found that it didn't actually have a sufficiently strong fence instruction, for example, to maintain the load-to-load ordering that the ARM example that I showed you a few slides ago had. So lacking that sufficiently strong fence instruction, there was no way to correctly compile many of the C-level litmus tests in a way that would actually run legally on some of the processors that were legal RiskFive designs. So of these 1,700 or so C11 programs that we tested, you can see the results that there were 2 variants of the instruction set available at that time, a base and a base plus atomic. And depending on which of those variants you were running on, you got some number of buggy outcomes. And I should stress that, you don't need a separate bug fix for each of the 144 buggy outcomes, right? So we're running a huge number of tests, some of which are pointing to similar shortcomings, for example, the lack of sufficiently strong fences. The takeaway was that spec as of when we did the study, couldn't serve as a legal C11 compiler target. The happy ending to this story is that over the past year, the RiskFive memory model group was formed to address these issues. It proposed what I think many of us consider to be a fairly clean and formally specified memory model that does compile C11 correctly. It just last week came out of its 45-day comment period, and so it seems likely to be ratified soon. And I think that's sort of a win-win all around. So, key takeaways. I am advocating strongly for formal, well-specified interfaces. I'm not a language designer, so I'm happy to take input on how we should sort of have the syntax of those things look, but I can show you from those sort of our experiences there how important it was to get the gist of sort of hardware details into some of them. So, I can also sort of crow proudly about the fact that since I'm basically an architect at heart, I'm not a verifier, and I was dragged, as I mentioned, unwillingly into memory consistency models. It is endlessly fun to me when we actually find issues that sort of warrant the verification we've been doing, and we found them across a range of different levels. Okay, I wanted to, in the last bit of time, talk about a second metric, which has sort of come into the news a lot this year, and that's security. Obviously, a lot of people have been looking at security longer than this year, but obviously, Spectre and Meltdown kind of brought it front and center for a lot of us. So, what is Spectre and Meltdown in a nutshell? Take an actually quite well-known cache side channel attack. The category of attack is called flush and reload. Combine it with an extremely widely used hardware feature, speculation. Come up with a fairly ingenious new exploit. So I would say many people knew that speculation might be vulnerable. Many people knew that flush and reload led to side channels. I think what was surprising to many people was the sort of efficiency and ingenuity of the particular exploit. And from that came these two new attacks, Spectre and Meltdown, and a whole bunch of scary news about them. Okay, so I would argue that when it comes to security today, it's a real example of sort of the looking where the light is good kind of problem. There's a lot of emphasis in the security community on kind of one-off discoveries and one-off fixes for things rather than more principled mechanisms for identifying, discovering, and defending against issues that come up in designs. So, in terms of sort of moving to a more principled approach, what we would like is to be able to specify a system to study in some formal way. We would like to be able to similarly specify the attack pattern or the class of attack patterns in some sort of formal or automatically analyzable way. And then we'd like to be able to synthesize or analyze some sort of some digested version of those two. So for the system and the attack pattern, either tell me what's possible or tell me that nothing is possible and I can sleep tonight. So what we did in my group in research that was led by Caroline Triple is we came up with our sort of initial versions of these steps. So we have an axiomatic specification that's supposed to say how hardware works. Even better, it's specifically supposed to say about ordering of operations, which actually is quite useful when you're thinking about these kinds of side channel attacks and vulnerabilities of the type that Spectre and Meltdown were. We came up with a way to present event sequences for things like flush and reload to a tool as happens before graph snippets. And then we could synthesize from that a set of analyses using relational model finding techniques. So we did that. We developed a tool to do this based on the mu-HB graphs that I already discussed. And we came up with some results already sort of September, October, November. But it's pretty natural once Spectre and Meltdown come out in January to say, well, wait a second, we have this tool. Let's see what happens. And within about a week of updating some of our axioms to reflect a microarchitecture that did speculation of the type that Spectre and Meltdown used, we were able to automatically synthesize the skeletons of Spectre and Meltdown. And we also synthesized 2 new exploits that actually use a different class of attack based on cache invalidation patterns rather than based on single cache patterns. We're also in an ongoing way applying these similar techniques to IoT systems right now, which have race conditions and concurrent accesses at a different granularity, but with similar attributes. So in summary, I would argue that the same sorts of interface specifications that we originally used for verification came in really handy in understanding security better and allowed us to move from anecdotal approaches to more comprehensive verification. And they also gave us leverage on doing full stack approaches from software through to microarchitectural details in a way that is, I think, increasingly important as people figure out ways to come up with security exploits that are very microarchitectural specific. So what's next? One of the things that's next for me is that right now a lot of our work is kind of 0 or 1. We find a bug or we don't. We synthesize a security exploit or we don't. What I would like to do is to move this towards more sort of quantified or statistical models for some cases. So for example, if we have a number of different scenarios that we can express as different happens before graphs, it would be nice to be able to express what's the statistical likelihood of different happens before graphs given a particular type of model. So rate the likelihood of something being observed, not just whether it could ever be seen or not. Within one of these scenarios, there's also some interesting work to be done on sort of quantification. Here, what we're looking at are coming up with not just A happens before B, but A happens a certain amount of time before B, or the transition from A to B has a certain amount of power dissipation associated with it, and so forth. What can you do with this? Well, it turns out that a lot of security exploits have to do with being able to sufficiently differentiate different scenarios in terms of their timing, but also in terms of things like the power side channels, where you're differentiating whether it's a high power or low power case. Thermal side channels, people are differentiating based on the temperature of the chip at different points. Even sound side channels, where they're sort of listening to the fan noise in a room and determining that. For all of those kinds of things, what we want is essentially an observer model that says, here's the differentiatability of these different scenarios. This is a 3-cycle cache hit, that's a 7-cycle cache miss, and so forth. Here's our sort of quantified low-level assessment of these different cases. And now you tell me your observer model. If your timing accuracy is of a certain level, you won't be able to distinguish these. If you have an old school millisecond timer, you won't be able to distinguish these. But if you have the ability to time at a finer granularity, you will be able to distinguish these. So it's about taking quantified measures of these scenarios and mapping them up against observer models that say what a given observer in a given situation could plausibly be able to observe. So overall, sort of coming back to this kind of dark picture, the goal of our work is to take more metrics and move them past the streetlight effect. So 20 years ago it was power, but now I would argue that it's security, it's verifiability, and so forth, and to sort of move us into a happier trail in the light instead. With that, the last thing I want to do is say thank you. The picture on the right is my current research group, and I love that picture, but it actually is missing some key people from this work. So the picture on the left is me and a chunk of my family tree from Micro last fall. So that's actually me, some advisees, some grand advisees, and some great-grand advisees. And with that, I'm happy to say thank you, and I'll take any questions.
Thanks, Margaret. This is Chen Ding from the University of Rochester. So I think I'm not alone in saying that microarchitecture is probably the street light that I have largely missed in the past work. Really, thank you for telling us this. My question a little bit on the TryCheck is that in the modeling, how much of the specification of the microarchitecture involves the memory subsystem? And then in general, how well specified is the memory subsystem, and whether there is anything that programmers should care about beyond memory consistency? So it's sort of two questions.
So let's see. So with a lot of our approaches, because they're fairly iterative speeds, we envision, and we typically use ourselves, a process where we don't drill down to detail until we decide we need to. And so our first tool basically had just a single blob of idealized memory. Over time, we came up with notions like the value and cache lifetime, the Vickel abstraction that let us handle hierarchical memory systems with coherence, without coherence, to considerable detail. I guess we haven't implemented a full coherence protocol with sort of transitional states, but we have done sort of pretty standard messy protocols and so forth. So I think increasingly, especially on the security side, what we're seeing is that the interaction of the memory system with the processor architecture becomes very important, both for correctness and for security and so forth. I would argue that doing a pretty good job of that early is more important than doing a perfect job of that late.
Hi, I'm Milan Kulkarni from Purdue University. I was wondering if I could ask you to maybe speculate a little bit. So if I were to take a big...
We're afraid of speculation now.
So if you were to take a big picture view, I could argue that in the 90s, PL folks and software people in general were really helped out by the architects because you solved all of our hard performance problems, right? Microarchitecture meant that things kept getting faster, the device people kept making transistors faster, so you made our lives easier. Going forward, especially when things like Moore's Law are starting to struggle, what can we do to make hardware lives easier? What can we do at the programming languages level?
So what can PL people do? A lot. So a lot of what our group has done is to take artifacts that already exist. Here's a processor, here's a compiler, here's some code, and sort of plug in axioms that describe that behavior, and then verify on the axiom side what's going on. Our last tool, the RTL check tool, is the one that actually tries to take the axiomatic and meet it up with an operational specification, namely Veralog. But for the most part, we're sort of operating on this side world of our own specifications of things that already exist. The natural flow would be for more of the specifications to be sort of an intrinsically generated part of the programming process, the design process, and the compilation process. And there's a lot of wonderful work in this community that's leading towards that. And we see our work as, in some ways, complementary in that sometimes sort of putting it off to the side and analyzing it as a side thing has allowed us to be maybe faster or to find different complementary bugs to the ones that have come out of other approaches.
Thanks.
Hello, thank you for the great talk. I apologize if you already sort of answered this, but what I was wondering is, in industry, like we've already seen the expense, I suppose, for major companies with Spectre and Meltdown and the changes they've had to make. And yet, you know, I still feel like they're not willing to fully put resources towards maybe advancing some of these security issues as we're seeing. I mean, this is still occurring at a research level. So what do you think it will take, or what do you think we need to do to, I guess, have industry start really putting a lot of resources into, you know, quantifying correctness and essentially, like, you know, backing this more fully, I suppose?
So so basically, what will it take for people to care about correctness and security? Great question. So in this talk, and sort of what I'm advocating for as a first line is to get us as designers really sort of mobilized around new metrics and new techniques to care about that. The next ring out is, I think, to get consumers to be more actively caring about it. When we gave them, so 20 years ago, we bought our systems based on CPU clock rate. It wasn't a perfect measure of performance, but it was a measure of performance that pretty much anyone on the street could say, okay, at the time, 500 megahertz is better than 300 megahertz. We know the subtleties that say that's not a really great way to operate, but still it was a pretty good shorthand. We don't have, I would argue, the good shorthands for helping to convey this to the outside world. And we need them, and we need them fast, because we're putting these processors and these systems into things that are very much safety critical, where the correctness is sort of going to translate to real safety issues. And we need a better way of conveying that, A, this is not an all or nothing thing. We're never going to have a perfect system that we deploy. And B, that there are these risks inherent that we need to be able to quantify better.
Hi, Roland Yap, National University of Singapore. It was a very nice talk. I think what you were showing was that the breakdown in the abstraction, that different abstractions don't quite match up. Then would there be an infinite regress, or do we need to close the entire loop somewhere on all the way down to the physics level or something like this, or not? Or is it that we just haven't been having the correct separation layer and not being careful enough with the correct layer?
So I think the question is sort of, what are the right abstraction layers, or are they going away entirely? I think one thing that we're seeing is we're moving towards higher level abstraction layers. So my sort of best example of this would be kind of TensorFlow API, and then sort of hardware accelerators all the way down underneath. So that's a much higher level abstraction than we've had in the past. I hope that we don't need to have everyone knowing all the physics of what's going on, because I think that will just overly stress a system that's already being challenged about how much you need to know at how many different levels in order to design a system that is performant and correct and so forth. Vikram, last question.
Hi, Margaret. I'm Vikram Madhve, University of Illinois. First, thanks for a very insightful talk. I really enjoyed it. You talked about a post-ISA world, and you gave several examples of why you think we're entering that kind of environment. But let me put this to you a different way, which is, or rather, let me put a different approach to you and ask you if this makes sense. It seems to me that a lot of the problems that you identified could be solved by using a virtual instruction set approach, where you have a compiler layer, you only expose a somewhat higher level instruction set architecture to software, and have a compiler layer, a translator or a backend code generator essentially, between that virtual instruction set and the actual hardware instruction set. And the GPU world has discovered this. So for example, you mentioned PTX, that's a virtual instruction set. HSA is a virtual instruction set. The Transmeta architecture was a virtual instruction set. They all have compiler layers in between what the software sees and what the hardware actually executes. It seems to me that addresses a lot of the issues you talked about, like heterogeneity, like the need to evolve hardware rapidly, the need to have diverse hardware at different price points. All of these could be handled using this approach, and potentially some of the reliability and security issues you've talked about also. So I'm curious, what do you think about that?
I figured when I saw you in line that virtual instruction sets were going to come up. And I'm a fan. One thing I will say is that the technical value of virtual instruction sets gets to some degree challenged by sort of the business ecosystem. That if different entities are trying to build their own stack, then they don't have as much of a motivation for their virtual instruction set to interoperate or even to be specified to the outside world clearly, to go up against sort of someone else's stack and someone else's virtual instruction set. And so it could be that what is a sort of good idea technically might get challenged by the fact that the companies tend to be organizing vertically to some degree right now as well.
I understand what you're saying. So the counterexample I would give to that is RiskFive. I think RiskFive could have been a virtual instruction set, and it would have not been caught up in the problem you're talking about, because it is trying to be an open standard.
I
And
have
I've argued
nothing
with
against RiskFive, but it doesn't cover the broad set of sort of system connectivity and integration issues that we need covered right now. It's very much of a traditional instruction set. And so I don't think, I couldn't quite understand the last bit of your question, but I don't think it is going to sort of morph into a virtual instruction set that will span areas usefully, because it doesn't have the sort of variation granularity, doesn't have the formal spec. There's things that it's missing. Yeah.
All right, let's thank our speaker.